let's take a deep look at the tangent function. Now the tangent function is the opposite over adjacent ratio that you're familiar with. And something to consider is what happens when you do that in your right triangles is essentially what you're doing is when you want the tangent of something, you're doing the y over the x value. And we practiced that a little bit in class. And in order to actually do the graph of the parent function, of the parent tangent function, we're gonna have to do a little work here. So I'm gonna start drawing some tick marks and I'm gonna label these in terms of radians. And again, I want you to think about what kind of characteristics might we see knowing that the tangent of an angle is really the y value divided by the x value. So let's look at how I scaled the x-axis. I went by pi over 2's, and at every even pi over 2, I rounded to a whole pi. So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, and I did the same on the negative side of the x-axis. Now, for tangent, whenever you get an x-intercept, in other words, whenever the graph goes through the x-axis here, y must be 0. So that's going to happen at 0, at pi, 2 pi's. So we're going to reflect it over here. There is some symmetry to tangent. So those are your x-intercepts, and that comes from the knowledge of the unit circle. Okay, so if I do the tangent of pi, what I'm really doing is the sine of pi over cosine of pi, because tangent is sine over cosine. There's another video I will have that explains that a little more in depth if you're sitting there wondering where that's coming from. And if you look at your unit circle, the sine of pi is 0, but the cosine of pi is -1. But that equals 0. So anytime I have a whole pi value, 1, 2, or -1, -2 pi, my tangent's always 0. Okay. Now, what happens at the pi over 2's though? Well, did you figure out what we might actually have here as an issue? At the pi over 2's, you actually end up with a vertical asymptote. Now, why is that? Well, if you break this up using what I told you up here, you end up with the sine of pi over 2 over the cosine of pi over 2. Now look at your unit circle. Sine at pi over 2, you're thinking, what's the big deal? Same as it's a 1. But what's the cosine up there? It's 0. That's undefined, right? That's an undefined value. So what happens in this case right here is we end up with vertical asymptotes. So what does this actually look like then? Well, what we have to do is we have to actually evaluate it at a pi over 4. And when we do that, we end up with the sine of pi over 4 over the cosine of pi over 4. And if you remember your unit circle, the pi over 4 angle is just root 2 over 2. But you end up with the same quantity divided by itself, which is 1. What happens is when you do positive pi over 4, which is about half of pi over 2, you'll get 1 and -1. And then the rest of the graph looks like this. Kind of like that. So this is what the tangent function looks like. And it's not like any of your other periodic functions that we've studied, sine and cosine. It is still a periodic function because it does repeat over regular intervals. Let's look at its domain and range and other characteristics though, because this is definitely very different than sine and cosine. First, let's talk domain. The domain on this is very interesting. We're going to treat it like we would rational functions. So what we're going to do is we're going to say it's all real numbers, except, and then we're going to state where the exceptions are. So when can we not, what x values can we not use? Well, let's look at our vertical asymptotes. We can't use any of these pi over 2's that are odd. So 1 pi over 2, 3 pi over 2, 5 pi over 2. You might be thinking, well, what about the even pi over 2's? Well, think about it. if I have an even pi over 2, so if I have 2 pi's over 2, 2 pi over 2, that just reduces to pi, and that's an intercept. So the even amount of pi over 2's are totally fine. So here's how we're going to say this. So we're going to say all real numbers except when x equals n pi over 2's, where n is an odd integer. Now range is super easy here because if you look at the directions of the ends of each of these pieces here, it's opposite directions, so the range is hopefully very clear to you that it is all real numbers. When does this have an x-intercept? Okay, well, it has x-intercepts whenever x is what kind of pi's. So we have 0 pi, 1 pi, 2 pi, and -1, -2. The pattern will repeat on either side. So we're going to say n pi's where n is an integer. Now, it doesn't have to be odd, right? Because notice 0, 2, they're not odd, but they count, they work. So we're going to just say where n is an integer. Let's see, it does have a y-intercept. Remember, it went through the origin. So the y-intercept is the origin. Tangent, let's see, it is always increasing. It looks kind of like a cubic function repeated over and over again. And lastly, it does have odd symmetry. Our periodic functions do have symmetry. Cosine has an even symmetry, sine has an odd symmetry, and tangent has odd symmetry. So here is our parent tangent function.